Greetings, math fans. All right, so this is our vector chapter, and let's just get started. So, vectors. So, some of you may or may not know about vectors. You may have taken physics and know a little bit about vectors. It doesn't matter. I can teach you everything from the ground up. Okay. So, first of all, our definition of the vector: it's an array that represents a magnitude and a direction. Okay, and let's talk a little bit about what each of those words mean. First of all, a magnitude is basically the length of the vector. And the direction is which way, real simply, which way the arrow is pointing. Okay? So, just to kind of give you an example here, if I have a vector, I have two parts here. I have, let's call this vector, this is A and this is B. Okay, so two types of notation we can have. So notation. The first is we call it a vector AB, and it's with a half arrow on top. That's a vector AB. Okay, and the A, we call this our starting point, but truly it's really called our initial point. That's more mathematically correct, initial point. Okay, and then B is our ending point. I'm going to put that in parentheses too because it's really called our terminal point. Okay, so it's got to be, A's got to be first. That's where you start, and you can just see that's the start of the arrow here, and the end is, it's really got a dot here at the end too. It's not like it keeps going. It actually ends at B. That's why it has a length. Okay. We can also label it. It's not as typical, but we can label this as vector x. So notation is a, b, or x, and this is okay, but it's not as descriptive. Okay, but we'll be using that as well. Okay, so far so good. These lines, so if I have A, B with those two lines on either side, they're not absolute value. Please don't use them as absolute value. That means the magnitude of vector AB. Okay, I'm going to put it in here, not absolute value. Okay, so please don't come up during the middle of a test and go, Mr. Curtis, is that absolute value? Or, because what I'm going to do is I'm just going to tell you to sit down. Okay, so boo, don't do that. All right, so a couple more things here. Two vectors are equal if they have the same magnitude and direction. Okay, so two vectors are equal if they have the same magnitude and direction. So here's the deal. They don't have to be next to each other. Let's say this is a vector. We'll call this vector A. And I want to make a vector that is exactly the same as a vector. I can draw it anywhere. I can draw it up here. I can draw it down here. Draw it over here. Anywhere in space, I can go 3D anywhere in space as long as the vector is pointing the same direction and has the same magnitude, the same length of that arrow. Okay, then they are equal vectors. Really, really, really important. So what I would do in class, which I can't show you now, is actually I'd hold up my eraser, and I would take the eraser and I'd keep it pointing in the same direction. I'd walk all around the room, all pointing in the same direction, bring it up to the ceiling, down to the floor, anywhere. If that vector is, if I haven't rotated that vector at all, or shrunk the eraser, okay, it's an equal vector. All right, very, very important. And then we have opposite. So we'll write this here, opposite vectors. Basically, opposite vectors have the same magnitude, but it points opposite direction. Okay, same magnitude, points opposite direction. So basically, here's an example. That and that. Okay, those are opposite vectors. Pretty simple. Okay. Again, a lot of little definitions I'm giving you guys today. The next one is a resultant vector. Basically, a resultant vector is the sum, S-U-M, sum of two or more vectors. Now we're going to learn two different ways to actually add vectors. The first method is we're going to use something called the tip to tail method. Okay, so real quickly, this is the tail and this is the tip on this part right here. Okay, just like a dog, right? I mean, if the arrow's pointing, in this case, it's pointing to the right, a little up, right? And so the nose, this is the nose of the dog right here, and this is the tail. Okay, it's in the back. All right, so let's talk about how you use that to add vectors. If you're given, let's say we're given vector A and vector B. Okay, and I ask you to find the resultant. Basically, you're going to add the vectors. And it's always tip to tail. So the tip of one vector goes on the tail of the other vector. Okay, so what I'm going to do is I'm going to draw, here's vector A. And this is the tip of the vector right here. I'm going to make it in red. It's the tip of the vector right here. Okay, and I'm going to attach it to the tail of the other vector, which is the tail of the other vectors right here. So it's basically, and I draw it the same direction because I'm adding it. So I don't do anything with it. So that's vector B. So that's tip to tail. Now here's the deal. This is so important. I'm asking you to find the resultant. Okay, so in order to find the resultant, this is your original starting point right here, right at the beginning of A, at the tail of A, and I wind up at this point right here, right, by B, right, at the tip for B. So my resultant is this vector right here. Okay, that is the resultant. Now something I cannot stress enough, and I'm going to highlight this here, is there's a couple things you need. First of all, you got to draw the arrow. Kids always forget to draw the arrow. They do this. So I'm going to show you the common mistake. This is what kids do. They go tip to tail. They go like this, and they go like this. And that's the answer. That's all they do. Okay, boo! Don't do that. Okay, you didn't do anything. You just wrote both vectors down there. Okay, you actually have to make that green vector as I have on my screen here. And you have to have, I can't stress this enough, right there, man, you have to have that arrow. If you forget that arrow, you will lose credit for that problem. Because you're not telling me, you're not really giving me a vector. You're just kind of giving me a line. Okay? It doesn't, I mean, think about it. If I give you a vector like this, and you add them together, and you give me a resultant that looks like this, a line like this, I'm like, well, which way is that arrow pointing? It's a line. It's a segment, technically. Okay? It doesn't do any good. So, the arrow is so huge. You want to write that on your paper, guys. Arrow is huge. Arrow is huge. Okay? And then, sometimes kids get confused on which way to draw the arrow. Guys, think of it, if you walk from school to McDonald's and then McDonald's to Lifetime, okay? And then somebody says, well, how did you really go? You said, oh, I went from school to Lifetime. Okay? So that's the old Lifetime Fitness, right? Hopefully this video lasts a long time and Lifetime Fitness is still there as the video goes on. But so your arrow goes from Conant to Lifetime, and that is how your arrow works. So from the start where you actually started, in this case here, our start is right here, and it ended, so we went from following vector A to McDonald's, and we went from McDonald's to Lifetime, and so this is our final destination. That's why the arrow points basically to the right here. Okay? Really, really, really important. That's finding a resultant vector. Okay? All right, so I got a little excited about that, but that's okay. You guys need to know how to do that. It's really, really important. So just kind of randomly, if I just drew another one real quickly here, if I had a vector like this and a vector like, let's say like this, and I want to add those together, it's this vector, tip to tail, that vector, and now I draw my resultant vector is this. Okay? Real, real simple. Just don't forget some of the little details there. Okay, so let's talk about scalar multiplication. Very scaly. That's bad. Scary, scaly. Okay. All right. Scalar multiplication is you change the lengths and direction of vectors. It's pretty easy. All right, so basically if I had vector A and I said, hey, what about 2A? Well, you just double the length. And guys, when you're doing this problem, don't be cheesy about it. Double the length of it and make it point in the same direction. So that is 1A, and that's 2 of them. So that is 2A. It's twice the length of that. It's pointing the exact same direction. If I said negative A means it just points, it's the exact same length, but it points the opposite direction. So that's negative A. Okay? Maybe a little bit longer. Make it look good there. Okay? So that is negative A. Really, really, really easy. Okay, so let's do a couple problems here with that. So let's say you're given A is that and B is, this is from just from like the last problem we did. Okay, so, or 2 problems ago. And B looks like that. So we'll make A a little bit longer. All right, so A is a longer vector, B is a little bit shorter vector, about half the size. And then I asked you to find a couple things. So I asked you to do 2A plus 3B. Well, 2A means 2A, so that's 2 of those, that's 2A, and plus 3B. Now, just because it's pointing down doesn't mean that's minus. That's the vector. So if I add 3B, it's 1, 2, 3. That's 3B. Okay? And then your resultant vector, again from the start, you're starting right here and you're ending up right here. So this is the answer. That's the resultant vector. You need that red line, actually red ray, make sure you have the arrow, and that would give you the answer. Okay? Pretty easy. Let's do another one here. How about A minus 2B? So again, what I'm going to do is I'm going to make, here's A, and it's minus 2B, so that means it goes the other way. So right now B is going down to the right. That means it's going to go opposite direction. So here, I'm going to draw it next to it. This is the opposite vector to B. Right? So that's why I'm drawing it up to the, going up and to the left. And I'm doing 2 of those, minus 2B. Okay? And then your resultant vector, remember this is your starting point and this is your ending point. So that is the resultant vector. Okay, and we'll do one more here real quickly. How about negative a minus 3b? So negative a, that means I'm going to point, let's so I can fit it on the screen here. And I go, this is negative a, right? And then minus 3b, well, remember I'm going this way for negative 3b. So negative 1b, negative 2b, negative 3b. Okay, and so again, this is my starting point right here. This is my ending point right here. And there we go. That's my vector. Okay, pretty easy stuff, right? Not bad, not bad. Okay. Let's talk about vertical and horizontal components. Okay, pretty easy. If this is my vector A, you basically have, you guys know this is the horizontal right here, component. Okay, and that's our x value, right? Because just think of it, it's x, right? It's like the x-axis. And then this is our vertical component, which is our y value. Really pretty easy. So we're going to be using, just because this is a right angle here, we're going to be using right triangle trig. Okay? So you're given, this is an example here, so given angle of inclination, if you guys remember, inclination is like an incline going up, an angle of depression, which is very sad. That's your angle going down. So angle of inclination, and it's always going to be from the horizontal. And that equals 40 diggity. And then, what is that symbol? Can't hear you, but I'm sure you're saying it is magnitude. That's very good. So the magnitude of vector v is 100. We haven't talked about units yet. We'll get to units actually in a little bit. So we'll just say 100 Schmutzkis. You make up your own unit. Okay. So v is equal to 100, and I want you to find the magnitudes of the horizontal and vertical components. Okay, so it's really easy. Again, if this is from the horizontal and this is 40 degrees, you're basically trying to find x and y. That's all you're trying to do. Okay, and then this is our magnitude is 100. All right, so we'll draw a little arrow here just to kind of show it's a vector. Okay, but it's really pretty easy. So we're just going to use right triangle trig, and of course, let's find y first. You know, y sin, right? So remember that sine of 40 degrees is y over r, so it's y over r. Cross multiply, and you get y is equal to 64.3. And that's our vertical. Okay, and then same thing, we're going to do cosine of 40 degrees equals x over r, so x over 100. Cross multiply, and you wind up getting x equals 64.3. And that is our horizontal component. Okay? Pretty easy. And real quickly here, math fans, if I ever ask you for a magnitude, magnitudes are always positive. Okay, they're always positive. Very, very important. Very important. So basically, I'm just going to cursor down here just a little bit. So basically, if I said instead of having this problem where it's 40 degrees, if I said theta, just an example, if I said theta is 140 degrees, what you're going to do is you're going to go, oh, okay, well, it's 140 degrees. So that's 140 degrees. Then really this angle here is 180 minus 140, which is 40 degrees. So you have a triangle over here instead. Now what's going to happen is, again, if I ask you for the magnitudes, you're going to do all the work, and you're going to have the exact same answers, right? Right? You're going to get everything the same because we're using 40 degrees. Now if I used 140 degrees and I took the sine of that, that's going to give me still positive. But if I took the cosine of 140, just like knowing all students take calculus, cosine is going to give you negative. But we know it all needs to be positive. So, sometimes you have to redraw it a little bit. If I give you 140 degrees, you draw it like that. If I give, 210 degrees, you're going to be down here. And so this is going to be 30 degrees. You're going to do all your work and get positive values with that 30-degree angle. And the same thing over here, right? Okay, so it's basically you're kind of getting a reference angle here. All right. Okay, so let's talk about units now a little bit. This is a pretty significant unit for force, which we're going to be using a lot. You'll use a lot in physics and also in this class as well. It's an important unit, and that is called a Newton. Okay, so Newton, of course, who was invented by? Sir Isaac Newton, right? Pretty brilliant guy. Just a little tip there, you hear about like Newton just came up with figured out gravity, right? And because he got hit in the head by an apple sitting under an apple tree. It's not true, actually. He got hit in the head by a fig. It's kind of weird. He's under a fig tree, and a fig actually fell on him and just hit him in the head. And he's like, oh, about gravity, it was all good. And then he actually brought the fig home, and they made a cookie out of it, and it became, it was a big hit actually in his town. It became the Fig Newton, and that got huge. And so then what happened is he sold it to Nabisco. Like, Nabisco is a really old company. He sold it to Nabisco for millions of dollars, made a ton of money on that, and so he's known for the unit of force and also for the Fig Newton. So it's kind of cool. I'm just kidding, actually. He had nothing to do with the Fig Newton. I just totally made that up. It could have been an apple that hit him. I don't really know, but I made that up, so don't write that down. That's why I didn't write it down. Okay. Anyway, it's a good story though. It's a unit of force, and basically it's to accelerate a 1 kilogram mass. So to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. Now you guys have heard like acceleration is meters per second squared, and the reason that's the case is because it's really acceleration is change in velocity, right? If you're doing 20 miles an hour and you hit your gas pedal and you're doing 25, you're accelerating. So you're changing your velocity per time unit. So velocity is like meters per second, and then you're changing that. So if it's change, it's meters per second per second. So again, this is velocity, and that's change in velocity per second, which is acceleration. Okay? So that's why it's meters per second. This is then squared. Okay? So that is what a Newton. Newton is a unit of force to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. Okay? Just very kind of important here. All right. So let's talk about another method, which is going to be pretty significant now. Another method to actually add vectors together. Okay, so this method is called the Parallelogram Method. And this is used a lot in bearing problems. Oh, I love bearing problems. Okay. Now what we're going to do is we're going to line up vectors. So it's a little bit different. We're going to line up vectors tail to tail. So don't get confused between this one and tip to tail. All right, that's it's not a good thing. All right, so let's just talk a little bit about it. So if I say vector A is, so this is actually the same vectors we've been using. Just to, if you ever want to look back at your notes to the old stuff, then it's a good comparison. So instead of doing tip to tail, what we're going to do is we're going to line up tail to tail. So this is what it looks like. So we have, here's vector A, and the other vector is vector B, and it's going to look like this. So that's vector B. So notice, I'm going to highlight this here, these are both the tails of vector A and vector B. We attach those together. Now what we do is we create a parallelogram. So we're just going to do that with dotted lines. So there's your parallelogram, right? Everybody okay with that, I hope? And then what we do is this where we connect it at the end. So we go from one corner to the other corner of the parallelogram. So this is the answer. Okay, the green line. So that is the parallelogram method, and you're going to see how that's going to come in handy actually, as we do some problems here. But a couple words here. Like I said, you make a parallelogram, then sketch the resultant. Okay, if I would have done a tip to tail, I just want to show you guys how it actually would have worked out really nicely. Watch this, tip to tail, and then we go down here, and then our resultant vector is like that, which is, you can see that this vector is really the same as that vector. Okay, just a different way to do it, but it's important that you guys understand how to do both, but don't mess things up. Don't try to do tip to tail by putting the two tails together. Okay, that's like really, really, really bad. All right, there are two different methods, and you gotta be good and not get the two confused. All right. So before we actually do one last problem here, we need to review some properties of parallelograms. It's really, really important to know these properties. So review properties of parallelograms. The first one is, you guys probably know most of these already. Opposite sides are parallel. Obviously, that's why they call it a parallelogram. Okay, second one is opposite sides are congruent. Remember, this is the congruent symbol. Third, opposite angles are congruent. Okay, and then the fourth one, which most of you may, I don't know, you might remember, maybe not, but this is actually super, super important as well. But consecutive, which means one after the other. Consecutive angles are supplementary. So real quickly, if I just draw a parallelogram here, kind of not that great, but if I add this angle and this angle, those would add up to 180 degrees. Okay, or if I add this angle and this angle, they'd be 180 degrees. Okay, but consecutive, so right after the other are supplementary. Very, very, very important. Okay? All right, so let's do a problem now. It kind of uses the properties of parallelograms. So this is my last example here, math fans. So if you have forces of 10 newtons and 15 newtons, you have those two forces, and the angle, so angle between the forces equals 50 degrees. And my question is to find the magnitude of the resultant. Okay? So you got two forces, you got the angle between them. So basically we're going to use the parallelogram method. That's the best way to do it here. So I'm going to draw one of them horizontally. It doesn't really matter. So here's a 10 Newton force. It just makes it a little bit easier to draw the parallelogram. So that's 10 Newton force. And then I'm going to draw it below it. I could draw it above it if I wanted. Doesn't really matter. But watch this. I'm going to draw a little bit longer because it's 15 newtons. And the angle between them is 50 degrees. Okay? That's my picture. And again, I drew these tail to tail. I'm going to use the parallelogram method. So what I'm going to do now is I'm going to finish up my parallelogram. Okay? And then I'm going to draw. It's not that good of a picture, but it's okay. I'm going to draw the resultant vector in there. Okay, now I'm going to use my properties of parallelograms to figure this out. So what I'm going to do is, you guys agree this is 15 newtons here. So this is also 15 newtons. And if this angle right here is 50 degrees, do you guys agree? Let's do this in, we'll still do green. Do you guys agree that this angle right here is 180 minus 50? Because this whole angle here is 50 degrees, and those are consecutive angles, so it's going to be 180 minus 50, which is 130 degrees. And so here I have everything I need now, math fans. I'm looking for that blue line. We'll call that blue line X. So let's actually just sketch it out here without all the other stuff in it. This is what I have. That and that and that. So I have a triangle. Of course, this whole year we've been working with triangles, okay? And that's exactly what we're doing here. So this is 10 newtons. This is 15 newtons, and this is 130 degrees. And I'm looking for X. Well, what are we using to find out X? Well, hopefully you guys are saying we're using the law of cosines. Certainly can't use the law of sines because we don't have an opposite angle or opposite side combination, right, ratio to do it. And so, of course, we're going to use law of cosines. So it's just going to be X squared equals 10 squared plus 15 squared minus 2 times 10 times 15 times cosine of 130 degrees. Okay, and I do all that work, take the square root, I get X equals 22.8 newtons. It's almost a full package of fig newtons. So sweet. Okay, so don't forget your units in here. Really pretty easy, but again, two forces pulling on an object. We're going to do some applications later on. But definitely using law of cosines. It's the only you can use to figure this problem out. But you got to use the parallelogram method to set up the problem correctly first. Okay, that's it, math fans. That's a good introduction into vectors, and not that difficult. Just some basic definitions and some basic setups, and you're kind of good to go. All right, that's it, math fans. Have an outstanding day. Adios. Goodbye.